Hello, everyone. In this talk, I'm going to introduce a new strictly serializable technique that achieves minimal overhead and avoids a correctness pitfall we identified in existing techniques. Many web applications are enabled by transactional data stores. Front-end client machines receive user operations like loading a page and translate these operations into transactions. Each transaction consists of a set of requests which are sent to the servers that have the data. The requests in the same transaction either all take effect or none of them do. Because data is sharded across many servers, concurrent transactions may interleave. So systems rely on concurrency control techniques to execute transactions in some order that satisfies the system's consistency guarantees. Strict serializability is often considered the strongest consistency. It requires transactions to take effect in a total order, and the total order must respect the real-time ordering constraints between transactions, which means if transaction 1 ends before transaction 2 starts, then transaction 1 must appear before transaction 2 in the total order. By enforcing these requirements, strictly serializable systems provide a powerful abstraction of programming in a single-threaded environment, which greatly simplifies application development. However, existing strictly serializable techniques require expensive mechanisms that reduce system performance. For instance, OCC requires extra rounds of messages for validation. Two-phase locking requires distributed lock management. And these techniques often incur excessive aborts. We find that these overheads are unnecessary for what we call naturally consistent transactions. Transactions are naturally consistent if their requests arrive at servers in an order that is already strictly serializable. Naturally consistent transactions are prevalent in data center workloads, where transactions are executed within a data center and then replicated across multiple data centers. In real-world data center workloads, many requests are reads, and it's OK for reads to interleave if they return the same value. Many transactions are short, reducing the likelihood of interleaving with other transactions. So this means many data center transactions arrive in a total order, and many of them also satisfy the real-time ordering constraints, because intuitively, a transaction that happens earlier in real time must arrive at servers before later transactions. So ideally, we could execute naturally consistent transactions simply in the order they arrive, treating them as if they were non-transactional operations, and strict serializability is naturally satisfied. By leveraging this insight, our new natural concurrency control allows naturally consistent transactions to execute with minimal interference, while also ensuring strict serializability. This makes strictly serializable transactions almost as cheap as non-transactional operations. NCC is enabled by 3 components: non-blocking execution on servers, timestamp-based consistency checking on clients, and decoupled response management. I will next explain each of these pillars in more detail. The client starts a transaction by assigning it a unique timestamp. Each server executes the requests from different transactions in the order they arrive, and updates their timestamps to match the execution order. The server makes the effect of each request immediately visible to later transactions, and buffers the response of this request, which will be sent to the client when safe, to avoid cascading aborts and ensure real-time ordering. Here is an example where transaction 1 reads A and writes B, and transaction 2 reads B and writes A. Each version is associated with 2 timestamps. TW is the timestamp of the transaction which created the version, and TR is the highest timestamp of the transactions that read the version. Transaction 1 has timestamp 4. The server executes its read by fetching the most recent version of A, which is A0, and buffers the read response, which contains the fetched version and its TW-TR pair. The server executes its write by creating a new version B1 and refines its timestamps to 5, which is greater than B0's TR, reflecting that transaction 1 arrives after the earlier transaction that wrote B0, and then buffers write response. Similarly, suppose transaction 2 has timestamp 8. Its read request fetches B1, even though B1 has not been committed, and extends B1's TR to 8, which is transaction 2's timestamp. Its write request creates a new version A1 and initializes TW and TR pair to its own timestamp, which is 8. So this refined timestamp reflects that transaction 2 arrives after transaction 1 on both servers. The buffered responses are decoupled from execution on servers and are returned to the clients asynchronously. When the client receives the responses, it runs the safeguard to verify a total order. In each response, the TW-TR pair represents a time range in which the request is valid. And thus, the intersection of the TW-TR pairs is the transaction's serialization point. That's it. At this timestamp, all the requests of this transaction are valid. For instance, NCC can commit both transactions at their intersecting timestamps, which are 5 and 8 respectively, while existing techniques like OCC may abort one of them. If the safeguard succeeds, then the client sends a commit message to each relevant server. If the safeguard cannot find an intersecting timestamp, the transaction may be aborted. The safeguard relies on timestamps to ensure the execution order is consistent. However, we identify a correctness pitfall where timestamps fail to guard against a total order that violates the real-time ordering constraints. As a result, the systems that execute transactions following their timestamps may violate strict serializability. We call this pitfall timestamp inversion. And here is a simplified example. The element removes Alice from access control. After transaction 1 is finished, the element notifies Bob of the removal of Alice through some channel external to the system, for instance, by making a phone call. Bob then uploads a new photo he does not want Alice to see. then transaction 1 is in real time before transaction 2, since it ends before transaction 2 starts. Meanwhile, Alice reads access control and the photo. One read arrives before transaction 1, and the other arrives after transaction 2. Suppose these transactions have timestamps 10, 5, and 7, respectively, which is possible since they are assigned by different clients. Then executing these transactions following their timestamps constructs a total order. However, this total order incorrectly inverts the real-time ordering constraints between transaction 1 and transaction 2. As a result, the system incorrectly allows Alice to see the photo she's not supposed to see. Timestamp inversion is subtle because it happens when a transaction interleaves with a set of non-conflicting transactions that have real-time ordering constraints. Timestamp inversion is fundamental as we find that it has affected multiple existing systems, and thus these systems do not provide strict serializability as claimed. NCC avoids timestamp inversion with response timing control, which disentangles the subtle interleaving by controlling the response time. Response timing control is designed to not interfere with non-blocking execution on servers. For instance, the access control server buffers transaction 1's response until its preceding read is committed, and then returns the response to the admin. This ensures that transaction 3 must arrive at both servers before the admin receives transaction 1's response, which is before Bob is notified, which is before Bob's transaction arrives at the server. This execution constructs a total order, which respects that transaction 1 is in real time before transaction 2. This figure overviews our system. The client assigns each transaction a timestamp, which is included in all the requests of this transaction. The server executes the request with non-blocking execution, and buffered responses are sent back to the client when response timing control says is safe. The client then runs the safeguard to check consistency and sends commit or abort messages to the servers, and meanwhile replies to the user. There are many other things to read about in the paper, including optimization techniques that reduce false aborts, a specialized algorithm for read-only transactions, and a mechanism for handling client failures. We implement NCC on ingenious code base. We compare NCC with existing strictly serializable techniques and those that provide weaker consistency, which present a performance upper bound for strictly serializable solutions. We run experiments under different workloads. So this figure shows the latency and throughput under the workloads that synthesize Google's F1. Y-axis is the read latency in log scale, and x-axis is the system's throughput. We show two-phase logging with two deadlock prevention techniques, wound weight and no weight. NCC is strictly better than OCC and two-phase logging. For instance, with reasonable latency, NCC achieves at least 2 times higher throughput. And NCC achieves much lower latency than OCC and two-phase logging. NCC also closely matches the performance of MVTO, which provides weaker consistency, while NCC ensures strict serializability. In this talk, we introduced natural concurrency control that achieves minimal overheads and guarantees strict serializability by leveraging natural consistency in data center workloads. In the process of designing NCC, we identified timestamp inversion which is a fundamental correctness pitfall in timestamp-based, strictly serializable techniques. Our evaluation shows that NCC significantly outperforms strictly serializable solutions and closely matches the performance of serializable techniques. Thank you.